So we'd like to have a high IPN, and the reason for this is it allows us to have a high peak power, it allows us for given power to operate in the linear range, and we'll see later it's going to give us a large dynamic range, which is good. And as we've seen throughout this, the way to do that is to have a lower gain at the beginning stages and high linearity at the later stages. But at the same time, we need to reduce the noise. And if you recall, the way to reduce noise in the system is to have high gain at the front. So we basically amplify the signal quickly and less noise at the earlier stages. So we see that the gain sort of conflicts with one another between linearity and noise. And what you need to do is simply do your calculations to make sure that you find the right balance in optimizing your system. So this is an example out of David Pozar's book. And it basically does a example for a whole receiver chain. And here we have gain, and then we have the noise figure, and then we have the OIP3. I'm just going to switch back to my color. And what I plotted here is simply the gain. And the way you look at this is I start off with my signal comes in at 0. That's my assumption point. And it gets attenuated by 4 dB. And then it gets amplified by 11. And attenuated by 2, attenuated by 1. And you can see each stage, as we go through the mixer and the filters, we lose, and then we amplify. And then we finally, at the end, amplify it up, and our total gain is 71 dB. So it's pretty easy to do a walkthrough of a receiver chain for gain. Let's look now at noise figure. The first thing we've done is we've actually, I'm going to write this out so you have it. This is your gain. This is your noise figure. And this is your OIP3. And so what we've done is we've converted these to linear scale. And the reason we've done that is you've got to have it in linear because calculating noise figure and OIP3 involves addition and subtraction, and you can't do that with dB. And so let's go and calculate this. And so it's pretty easy. The noise figure of, I'll just go ahead and write this out again. This is the noise figure that we're going to focus in, and here's the gain. The noise figure, the first stage is 2.5. That's easy. If we go here at the second stage, it's going to be 2.5, and then we take 1.6 minus 1. Remember, we're subtracting 1 because that 1 is the input noise. And we are going to divide it by the gain of the first stage, but the gain of the first stage is a loss of 0.4. So we divide it by 0.4, we get 6 dB, and then we carry on through the mathematics, and what you notice is after the fifth stage, so here's 1, 2, 3, 4, 5, when we get to this point, our noise figure, the equivalent noise figure, really hasn't changed much. And the reason for that is because of the high gain at the input. And so if you plot the noise figure in a receiver, it will tend to just level off and not increase. And it's the first two stages that really dominate. First 1 or 2 stages that dominate the noise figure. And that's because the first couple stages amplify the signal, and once it's a large signal, the noise that's added by the future stages is always really teeny. And so if your signal's large, then adding a little bit of noise isn't going to affect it that much. And now I want to look at IP3. And so here is our OIP3 at our output. So we start with calculating the OIP3 here, and we see that first off we take the OIP3 of the last stage, and it's 1 over that, which is 5. And then remember we need to take the first stage, and we're going to take the gain, 12.6, and we multiply it by the OIP3 of this. Now this OIP3 here is listed as 1e to the 10. And what this is basically telling you, this is a linear filter, and there really is no nonlinearity about it. So it's a very high OIP3, basically telling you that you can put as much power as you want into it, and then quite frankly until it burns up, it's going to be linear for you. And then as we move on to the next stage, once again the OIP3 is almost infinite for a linear filter. I take my 5 and now I multiply it by my gain, and then I take the 2 gains of the previous stages by the OIP3 of my first filter, and I go through the math. And what we notice is that it's not like noise figure was. We've plotted it down here. And you can see it kind of moves around a bit. it doesn't do like gain. The gain went up decisively, and the noise figure stayed about the same. And the reason for this is that OIP3 depends upon the actual elements later. So the reason we end up here, we could have easily ended up here or down here. And you can see it's quite variable, so we can't make the same assumptions that we do about noise figure that only the first couple stages are going to matter. We really do have to do the calculations and make sure it all makes sense.